This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Our next speaker is Nayeli Rodriguez Briones from Technical University in Vienna, and she will talk about improving machine learning via quantum refrigerator, meaning we are going to get a little bit of quantum thermo angle on the QML. Great. Okay. Whenever you're ready, Nayeli.
Yeah. Can you hear me? Okay. Yeah, thank you very much for the kind introduction. And I'm very happy to have the opportunity to share the big picture, or at least a flavor of the research that I have been doing in collaboration with Professor Daniel Park from the Yonsei University in Seoul, Korea. And what I'm going to describe is how you could enhance quantum machine learning by cooling physical systems. So let's go back a little bit to the main goal in the quantum machine learning. So what we want to have is enable quantum systems to have the ability to learn from data and then apply what has been learned to new situations, what is also known as the generalization. But this is also offering very fascinating opportunities for fundamental questions in physics. For example, what would be the limitations that you have for learning? What are the limitations that come from physics about generalizing? And it's also very exciting because you already have a lot of tools that come from the quantum information processing. So that will help you to have unique opportunities. And as you know, also the quantum version has their own unique challenges. So along those lines, the key questions that we have been addressing is how you could bridge quantum machine learning with some of the important results that already exist in physics. And in particular, we want to use insights and techniques from quantum thermodynamics. And before presenting the main tool that we use, I just want to give a little bit of like a primer about what's the type of problems we care in this. Like to start simple, so we are going to first focus specifically in the quantum supervised learning. So as you know, you have the setup as a number of set of data. So for example, here you have matrices that are associated with the input, and each of them is going to be labeled. And just to make it simple, let's assume that you have a binary label, -1 or +1. And here, a very simple prediction function comes from the sign. So you could say it could be +1 or -1. And there are many examples of methods that tackle this type of problems. Just to pick an example, and it would apply to any other, but just to have like an example of how it would work. In the variational quantum algorithm, that is the example, this prediction function is given by the expectation value that you have by measuring a lot of qubits at the end after you process your input information with a parameterized unitary. When you have this binary scenario, these measurements, the only requirement that you need is that they have a distinct eigenvalues. So you could have this distinction between the +1 and the -1. For example, any of the Pauli matrices would be sufficient for this type of classification. And for picking one of them, let's say that you take the set Pauli. So this prediction function that you will have from the expectation value is going to be given by this line in the bottom. And as I said, there will be many other examples to what I'm going to say. The next slide is going to be applicable. But in all of them, they have that this binary classification could be framed in the same type of problems of having one qubit measurement. So we have, let's think how we could rewrite and how it's going to be simplified by taking, for example, the set Pauli measurement. So without generality. Like you could always have a single qubit written in this form, so you need 3 real parameters, and in this form, actually, they represent the projection in the different axes in the Bloch sphere. So this classification rule, in this case, will be simply by seeing what is going to be the alpha. You see the parameter that is just in front of the set. So it's going to be simplified just to give for a new data with the optimal parameter, you will assign +1 if this alpha is positive, or a -1 if the alpha is negative. So in this case, the challenge that will happen in all the methods that you have in the quantum version, that actually doesn't happen in the classical, so this is somehow a problem that comes from the quantum machine learning, is that you are relying in the expectation values. So you will need to measure and have a lot of repetitions until you have like a good mean sample that comes like close to the expectation value. So the question that we want to improve or we want to address is how you could reduce this probability error that comes intrinsically from the nature of quantum. And first, let's see actually what is this probability error. So that comes through the basic statistics. So the relationship that you have between the error and the number of repetitions